This video is about simplifying radicals. So I'm going to show you some examples about general simplifying, some examples of multiplication, and some examples of division. Very important in this lesson for you to be familiar with the perfect squares. For example, it would be nice if you can memorize that, 1 to the second is 1, and 2 to the second is 4, and 3 to the second is 9, 4 to the second is 16. I'm going to put the basic ones down. (64). 9 to the second would be 9 times 9, which is 81. 10 to the second would be 100. 11 to the second would be 121. And maybe I could squeeze in there 12 to the second, which is 144. Yeah, there are more, but this is like a basic list that you need to identify or be able to identify right away. So memorizing them would be very beneficial. And please remember that square root of 1 is 1. That's square and square root undo each other. Square root of 4 would give you the 2. Square root of 9 would give you the base, which is 3. Square root of 16 would give you 4. Square root of 25 would give you 5, and so forth. So it is very important for you to be able to identify numbers from this list. So if you don't know them, if you haven't memorized them, please take some time and do so. It would make your life so much easier. Let me go and start some examples on simplifying. So the first one that I'm going to go over with you is square root of 42. So you're trying to find perfect squares that are in 42 so you can pull them out, and that's what means when we're saying simplifying them. We don't want a decimal. We know that we can all put this in our calculator to get the decimal, but that's not the intention of this exercise here. So I'm thinking about 42 and like the perfect squares that are lower than 42, and none of them fits evenly or divides evenly by 42 except 1. So I would say there's nothing else I can do here. So I would just, it is equal to square root of 42. So the only way for me to replace it would be 1 times 42. And there's nothing else I can do there. Not a perfect square in there. Let me go to another example, which might be a little bit more interesting. Square root of 8. All right, so going to perfect squares that are below 8, I can replace the 8 with 4 and 2. Now, square root of 4 is 2, because 2 times 2 is 4. I'm stuck with that. There's nothing I can do. So there's my answer. So square root of 8 is equal to 2 square root of 2. I pulled out every perfect square that I could. So it doesn't mean that at the end we're going to be done with all the square roots. No, but we have pulled out whatever we could from that specific number. Let me go to another example. Square root of 144. Now, this is really a perfect square because square root of 144 is 12. If you know the rule from before, if you know the column, because 12 times 12 is 144. So very rarely you might be given a perfect square and you just put that perfect number down, the integer. Another one, let's see here. How about if you have something like this? A number and a radical. So remember, radical means square root. Now, the number has nothing to do with the radical. They're not like terms. So what I'm going to do is I'm going to leave the number there, but I'm thinking about the radical. I'm thinking about replacement. And if you go over your list of perfect squares, 27, I can replace it with 9 and 3. Negative 5 stays there. Square root of 9 is 3. So that comes out. Don't put the square root again because you can clean that out. But you're stuck with this. So your final answer is, now you have integers here. They're both factors and you can multiply them. They're like terms now. So negative 15 square root of 3. So this became this. I pulled out every perfect square that I could out of 27. One more than simplifying here. Let's do, how about if we do 2 square root of 50? All right, 2 stays there is a factor. I'm thinking about replacing 50. The biggest perfect square in 50, I need the biggest, so I can finish the problem right away. I'm replacing it with 25 and 2. 2 stays there. Square root of 25 is 5. And there's that. These are factors out of the square root, so they're like terms that I can put together. 2 times 5 is 10. So there's my answer of that. So again, from there, I got to here. I pulled out any perfect square that I could out of 50. Let's do some problems with multiplying, some examples. What about if you have something like this? Square root of 4 times square root of 4. I did say before that square and square root undo each other. So if you agree with me, you have two of the same, right? So I can write it like that. 2 square root of 4 to the second. The square root and the square undo each other. So this is really 4. Or, another way to think about this, because they're both like terms, they're both under radicals, I'm allowed to put them together. 4 times 4, it's 16. So I'm allowed to do that because they're both under square root. So square root of 16 is really 4. So no matter how you do it, your answer would be 4. Another one, let's do 2 square root of 3 in parentheses times 3 square root of 6. Now here you have two of the numbers are just plain factors, so you can put them together, and then the other ones are radicals. All right. Well, I can do 2 times 3, which is 6. Now, for the radicals, I have some options. One way to do it is I can put them together and then move on from there. Replacement for 18, the biggest perfect square is 9, so I can do 9 times 2. 6 stays there. Square root of 9 is 3. Comes out. I'm still stuck with the square root of 2. So finally, 6 times 3 is 18 and square root of 2. And that would be my final answer. Another way to look at this problem, from here, I can do, let me just write here, or I can do 2 times 3 was there. Square root of 3 is 3 is a prime, and I can bring 6 down to its prime factors. So I have 2 times 3, I have 2 square root of 3's, which means square root of 3 to the second. So the square root and the square undo each other, and I'm still stuck with the square root of 2. So that would be 2 times 3 times 3 times square root of 2. 6 times 3 is 18, square root of 2. So guess what? I got the same answer. Number 3, a third example here. How about if we do negative square root of 5 times square root of 20? Again, I can just show you a couple of options here. One option is because they're both under radical, I can put them together. The negative stays there. 5 times 20 is 100. And of course, 100 is a perfect square. So negative is my answer, and square root of 100 is 10. So there's my answer. Another way to think about this, as I did before the second method, it would be negative. 5 is prime. 20 can be equal to 4, square root of 4 times square root of 5. Negative stays there. I have 2 square root of 5's, right? So 2 square root of 5's are going to give me 5. And square root of 4 is 2. So that's going to be negative 10 again. So there are more than one way sometimes to get there, but the idea behind this is you better get the same answer. I prefer kind of like the method that will get me there with the least amount of steps. That's what I prefer. Here's another example to go over. How about if I have square root of 15 times 3 square root of 5. So 3 is a factor. It's not under square root. Here's what I can do. I can bring the 3 up front. I can break the 15 to its prime factors. And I still have a square root of 5. All right, so 3 stays there. I have 2 square root of 5's. So that's going to be equal to 5. Because square root of 25 is 5. But I'm still stuck with a square root of 3. So it looks like the final answer is I can put those two together. 15 square root of 3. Let's do one more here with multiplication. How about if you have something like this? 4 square root of 8 times square root of 2. One way to do this would be 4 times square root, if you put them together, of 16. And of course, 16 is a perfect square, so it's 4 times 4, which is 16. Or, here's what else you can do. You can leave the factor of 4, break down the 8 into its equal, and you still have another square root of 2. So here's what's going on here. Well, 4 stays there, square root of 4 is 2, and you have 2 square root of 2's, which are going to give you a total of 2. Multiply all those factors. 4 times 2 is 8, 8 times 2 is 16. So you got the same answer. 16 and 16. Let's go and show some division examples now. Be careful with division and remember what we have said, or what was said in the previous video, that we cannot leave our final answer with a radical or the square root on the denominator. So square root of 8 over square root of 7. Can I just try to make this line smaller? There we go, or lighter. All right. So we call this rationalizing the denominator. So in order for me to get rid of the square root, here's what I can do. Rewrite what you see and multiply both of them by square root of 7, which is the denominator. Now I'm allowed to do that. I'm rationalizing the denominator because square root of 7 over square root of 7 is really 1. So I'm multiplying this by 1, and I'm still going to, anything times 1 is that not that same answer, right? So I'm not switching the value of the problem. So here's what I have. On the bottom, I'm going to get square root of 49, which is really 7. Or you can think about it, 2 square root of 7, which is 7. On the top, you have some options. Maybe you can break apart the 8 to 4 and 2 square root. And there's nothing you can do with the 7 as far as breaking it apart because it's a prime number. There's not a perfect square other than 1 in it. Square root of 4 is 2. And 2 and 7, nothing else. So might as well put them together because you're getting ready for the final answer. Here we go. So I'm done because my final answer does not have square root in the bottom. And moreover, under the square root, I don't have any perfect squares anymore. Number 2, let's do square root of 2 over square root of 6. Okay, I'm going to rationalize the denominator again. So rewrite, and the denominator is helping you and it tells you what you need to multiply by. The same thing top and bottom, which is equal, a fraction equal to 1. On the bottom, 2 of the same gives you, get rid of the radical, 6. On the top, here's one way to do it. 2 stays like that, but I can break apart the 6 with 2 and 3, of course under square root. Square root of 2 times square root of 2 is really 2. This stays there. And at this point, be careful, you're not done yet because 2 and 6 are multiples of each other. So I can simplify top and bottom by 2. And I'm going to have this. This will be the best answer. It's completely simplified. If you stop here, you're not completely simplified because you're sharing common factors. We want to completely simplify. Here is another example. Square root of 21 over square root of 15. Now, when I'm dealing with big numbers, I prefer breaking it down to prime factors as I showed you before. So, for example, this can be square root of 3 times square root of 7. And this could be square root of 3 times square root of 5. Well, square root of 3 and square root of 3 are the same factors exactly, the same thing. So my final answer for now is this, but I'm not done, of course. There's a problem because on the bottom I have square root. So now I'm going to do rationalizing the denominator, which means multiply top and bottom by that, by the bottom. The bottom is 5. And there's nothing I can do on the top because 7 and 5 have no square roots, no perfect squares in them other than 1. So because I'm almost done, I'm just going to put it together. That's it. People don't say 35 divided by 5 is 7. No, this is not 35. This is square root of 35, which is different from 35. There's a big difference there. So that is all I can do for this. Let's move on to number 4. How about if we do this? Square root of 15 over 3 square root of 6. So I try to make my numbers as small as possible first. So let's see here. I can do the top. I can do 3 and 5. and on the bottom the 3 stays there, and I can do the 6 as 3 and 2.